that will be a solution. Maybe often you'll decide, do I keep it, do I not keep it? Or maybe you have to color it, maybe you have to assign a value to it. Who knows? You need to make a decision about each. And after you've made a decision about every object, then you have, that is either a valid solution or not a valid solution. And if it's a valid solution, then there's an easy to compute cost of that solution. Often the cost will be the sum of the cost of the objects that you've kept, but it could be any cost, right? And then your goal is to find a solution that's optimum, that is the best solution, or either the highest cost or the lowest cost, depending on which you're doing. So what's the algorithm? The greedy algorithm is you look at each object by itself. You don't look at the entire input. You look at each object by itself. The lion. How much do I like a lion? And you assign a priority to it without knowing what else is there. And then if you're doing a non-adaptive algorithm, later we'll talk about adaptive algorithms, but a non-adaptive algorithm, you assign a value to each object and you sort the values according to that value, and then you grab the best one. You go through them in order. And as you grab them, you have to make a decision about it. And usually the decision will be, yes, take it. Right? Why? Because it's the best, unless you have a good reason not to. Right? If the decisions you've made so far means that you can't keep this thing, or else it won't be a valid solution. Right? So the concrete example we're thinking about is your objects are quarters, nickels, dimes, and pennies, and you have to keep a subset of them, and it's a valid subset if it adds up to 92 cents, and the cost of a solution is the number of coins, which we're trying to minimize. So the algorithm we were looking at is you grab quarters until another quarter would add up to too much, and at which point you throw away the rest of the quarters. And then you do the same with the dimes. Right? And if we're going to use a loop invariant sort of idea, we need a loop invariant. We need to say, okay, I've looked at some objects so far, and I've made decisions about those objects, and those I never can change. I've committed to those decisions. And how do I know I haven't gone wrong? This is the first thing you need to memorize, right? Well, I guess everything I said so far is pretty useful. But this is, you definitely need to know this loop invariant. Right? The loop invariant, the first sentence is just kind of a casual thing. I haven't gone wrong yet. And what does that mean? The formal thing is there exists at least one optimal solution consistent with the choices made so far. Right? And what does that mean? Well, I've made choices so far. Right? I've said, take this, don't take this, take this, don't take this. Or paint this red, paint this purple. Now that's not a full solution. A full solution makes a decision about every object. Right? There's some way of making a decision about every object that's consistent with what I've done so far, and that is optimal. Alright? Now what somebody asked as we were leaving last class is, well, how can you possibly do this when you don't know what's optimum? Right? We don't know what an optimal solution is. We don't know the value of an optimal solution. Right? So it seems like an absurdly hard thing to loop invariant to maintain, yet we will maintain it nonetheless. Alright? So everybody get what the statement is. Any questions about what the loop invariant is and what the algorithm is? Right? So if I've committed to 2 quarters, thrown away the rest of the quarters, and committed to a dime, then I know that the loop invariant says there exists an optimal solution that contains exactly 2 quarters and at least 1 dime. Right? Does that make sense? Now there may be a solution that contains 5 quarters, right? And that's okay, as long as there's at least one optimal solution that contains 2 quarters. Right? It's okay to burn some of your bridges. It's okay to say, hey, when I make this decision, some optimal solutions, some solutions are no longer possible, right? If I take the lion, then I have a lion. I no longer can have zebras. That's just that's the way it is. But so I've burnt some of my bridges, but I haven't burned all my optimal bridges. So the first step is how to establish the loop invariant. Right, we're at the beginning of the algorithm. We say, you know, if we're writing up the solution, we say, hey, we're now doing this step here. Precondition code gives you loop invariant. Precondition is what? The precondition is I have a bunch of objects and I need to find an optimal solution for them. Right? Precondition says, hey, I haven't made any decisions yet. Right? So, is the loop invariant true?
Yes.
Does there exist an optimal solution consistent with the decisions I've made so far?
Could you have a situation where there is no possible solution?
Very good. Very good. I was just going to raise that point, right? So, the question is it possible that there's no optimal solution? All right? Well, there are problems. Well, let's first say, if there's a solution, then there's an optimal solution. Right? Everybody follow that? So, the question is there a solution? Well, for most problems, there's trivial solutions. You know, the don't take anything solution is a solution. Now, for the 92 cents, you know, if we didn't have pennies, you know, there wouldn't be a solution. Right? So we could do the same sort of thing like we did for binary search or something, right? The binary search says, you know, you're narrowing the search space. It says, if there's a solution anywhere, then there's a solution here, right? We can do it. That's basically what we're doing here, is we're narrowing the search space. We're saying, if there's an optimal solution, then there exists an optimal solution consistent with the decisions we've made so far. Right? People remember the narrowing the search space idea and see how this is sort of similar to that? Yeah? All right, so I didn't write that in, but sometimes it's an issue. Right, so that's just what I said. Initially, we haven't made any decisions, so assuming there is a solution, there's an optimal solution, and since we haven't made any decisions so far, that optimal solution would be consistent with what we've done so far. All right, so now this is clearly the harder part. If you know, this is our step, we're doing our test. We write down now we're doing this thing. You know, if we have our loop invariant, we have the excellent conditions not met. We do some code. We have to then do some code that makes progress while maintaining the loop invariant. You've heard these words before. So, what does the loop invariant tell us? Loop invariant tells us we're at the top of the loop. The algorithm has made some decisions so far, and there exists an optimal solution consistent with those choices. Right? Do we know what the optimal solution consistent with these choices is? No, we don't know what it is, but we know that it exists. It's an existence proof. Right? But that doesn't stop us from giving it a name. If you want to talk about something, if you want to have power over something, you know, and you're a wizard, the first thing you do is you give it a name, or you learn its name, right? So here's the name. Let's call it optimal solution sub loop invariant. Why? Because it's the optimal solution that we know exists from the loop invariant. Right? So then, what does the code do? Well, we know the code. The code looks at the next best object and either commits to accepting it or rejecting it or painting it blue, right? And then, now we have to prove the loop invariant again. And what do we have to do? We have to prove that there exists an optimal solution consistent with all of the choices. Now, what are the choices that have been made? There's the choices that were made before, and there's the new choice. Right? Because when we were at the top of the loop, there were already choices that were been made, and then there's this new choice that was just made. Now, how do we prove that? Well, we have to prove that there exists an optimal solution consistent with the choices. And the way we prove something exists often is we construct it. We construct an optimal solution. But that's kind of hard to construct an optimal solution when we don't know anything about the optimal solution. We don't know the cost of an optimal solution. Right? But what do we have? Sort of. We don't really have it. we know the existence of this optimal solution. Right? We pretend that we have it. We don't actually have it. We pretend that we have it. And from this object that we know exists but we don't have, we say, let's change this into something else. Right? We come up with a little method of changing what we don't have but we think we know exists into something else which we don't have but we now prove that exists. And then we have to prove that this thing that we constructed, we have to prove that it's a valid solution, meaning that it doesn't have any conflict. In this case, it means, what does it mean to be a valid solution in our example? Adds up to 92 cents. It's a set of coins that adds up to 92 cents. We have to prove that it's consistent with the previous decisions that were made before and consistent with this new decision. What does that mean? Well, when we were at the top of the loop, the algorithm had made some commitments about decisions about a certain object, and then we went around the loop one more time, and we accepted or rejected this new object. So this thing that we've constructed has to be consistent with both the new and the previous decisions. And we have to prove that it's optimal. Right? And then once we've showed how to construct this thing from this thing, then the bottom line is, well, we know this exists from our loop invariant. We know that if this exists, if we had this, we could construct this, and which would prove that the loop invariant was true. Now we don't have this, but we know it exists. Right? So we know this exists. People kind of following that a little bit? Now we're going to go over examples of this and talk about it, but this is what you need to be able to do and understand, and you should have to learn these steps.
So what's the relationship again between the loop invariance and our special thing, our optimal solution? Like how do we, what I don't.
Right. All right. So one thing that I really recommend you working on is keeping track of, if you're doing computer programming, one thing that's useful is type checking, knowing what everything is. All right? So for example, this is a solution. What does that mean? It's a decision about every object, right? Every object, right? And this is a type of solution too, right? And what do we know about this? Well, our loop invariant tells us that such a thing exists. And what is it? It's an optimal solution that's consistent with all the decisions that have been made previously. Right? So, right, here are all the objects. And, so far we accepted this one and rejected this one and accepted this one. Right? That's what the algorithm has done so far. What is this? Well, it's a decision about everything, right? So it maybe accepts this or rejects this. Well, what about these? It has to do the same with those, right? So what is this thing here? It's a solution, meaning it makes a decision about every object. It's valid, meaning that all the check marks add up to 92 cents, and it's optimum, right? So, any questions right now?
Okay, so are we changing that loop invariant into our own solution, our own optimal solution? So are we changing the bottom row?
Yes. Let's go. Let's let's do a few more slides. Keep it. So, I'm going to talk about. I like telling stories with players and people. Some people really like my stories and some people don't, right? Some people get all upset and talk about the existence of God and the existence of fairy godmothers and stuff. And if you find the story useful, then you can run with it. Otherwise, you can do all the steps without ever mentioning fairy godmothers. All right? But I do think that they're useful, and I think it's useful to try to think about what is it that people get wrong often when they do these questions. And how, if you keep track of these players, it helps to understand what's going on. All right? So I have 3 players. The first player I think of is my little brother. He's the algorithm. And what he does is he's pretty stupid. All he does is he grabs the next best thing and he decides whether to keep it or not. Right? And we know what he does. Right? We know what his role is. We know what he knows. Right? He just grabs the next best object and decides to keep it or not. And that's all he does. Right? The next player is the one I think of as me, the prover. My goal is to make sure that my little brother doesn't get into trouble. I have to make sure that the loop invariant's maintained. Right? You'll note that the difference between these guys is that the algorithm, the prover is going to do lots of hard work that the algorithm doesn't do. Right? The algorithm, the prover proves all these things and moves around optimal solutions and does really weird things. The algorithm doesn't do that. So one first place that people get confused is if you were to ask to code up the algorithm, they want to code up what the prover does. Well, that's not part of the code. Right? The algorithm, really all it does is it looks at the next best object and keeps it or not keeps it based on very trivial things. Right? So the reason we split these two guys so that you keep track of what does the prover do, what does the prover know, what does the algorithm do, what does the algorithm know, and they're different. Right? Does that make sense so far? Now we're getting a little bit more oh yeah, dumb brother, yeah. I make sure he doesn't get into trouble. All right, we're getting a little bit more, oh yeah, yeah. I said that already. All right, so now we're getting a little religious here. All right? This is the fairy godmother, and people will ask, does she exist or does she not exist? And I can't answer those questions for you. All right? All right, now what is she doing? We know that there exists an optimal solution out there, but we don't know what it is. Right? And we need to change that. We need to manipulate that hypothetical optimal solution out there, even though we don't have it. So it feels very weird to say that we have something or we know about something, but we don't have it and we want to change it, although it doesn't exist. You know, we don't know where it is. It's all very weird. So we're going to talk about this in terms of there's a fairy godmother out there somewhere, and she is holding our optimal solution for us. She's holding a witness that there exists an optimal solution consistent with what the algorithm has done so far. All right? So the algorithm has committed to some objects, and the fairy godmother is holding this optimal solution for us. Right? So we can now talk about it. She has it, has this name, she's holding it. What's her role? Pretty well, that's her whole role. She holds it. Right? Now, what communication happens here? Well, the algorithm does something and the prover knows it. The prover, this is where it gets kind of weird. The prover can talk to the fairy godmother, right? Just like you can talk to God. But fairy godmother, as far as I know, never talks back. Right? It's a one-way communication. So does she exist? Does she serve any function? You know, I don't know. Right? Everybody kind of get what we're doing here? All right? So the point of her is to emphasize the fact that the prover is going to be talking about this object but doesn't know it. Right? Doesn't know what it is. Right? He knows he's talking to it, but he's changing it, but he doesn't know what it is. So it separates out what people know. She gives no feedback, right? So does she exist? I don't know. Right? She could exist or not. All right, so now let's go through an example. Right? Let's start off with here's our input. There's all the objects. Here's the fact that it adds up to 92 cents. Here's our 3 players. Right? And the first person to go is that, you know, maybe we've gone through 2 iterations. We're at the top of the loop, and the prover, the algorithm says, hey, I've committed to these 2 quarters. Right? Those 2 quarters are going to be in my solution. And the fairy godmother, you know, she thinks or says, or you know, you trust in her, that she has here an optimal solution. If you'll note, if you add up those coins, it adds up to 92 cents, and if you play around, you see that it's optimal. And you note that she has the quarters that the algorithm is committed to, so it's consistent with what the algorithm is committed to. Everybody see what we got so far? And of course, as I say, these guys don't know what that optimal solution is. Right? So now, we go around the loop, and the algorithm looks at another quarter and commits to it. Right? So he commits to that. All right, so we have a problem yet? Everybody good? All right, so just for the sake of this argument, let's say that these quarters are unique. So if you take a different quarter, you have a different solution. Right? So my job as the prover is to prove that there exists an optimal solution consistent with this quarter, and this quarter being taken. Right? I have to prove that such a thing exists. I know that the fairy godmother is holding an optimal solution consistent with having this quarter and this quarter. But I don't know anything about this quarter. Right? People with me here? Right, so how am I going to do it? I'm going to give instructions to the fairy godmother as to how she should change her optimal solution. And I trust that if those instructions are, the instructions have to be such that she's always able to do them. I can't tell her something like, oh, give me an optimal solution, because I don't know she's able to do that. I only can give her instructions that I know she's able to carry out, and I trust she'll carry them out. All right? I'm going to tell her how to, I think my old book the version talked about massaging solutions, and I don't think the publisher liked it, so I don't think it says massage anymore. Somehow it manipulates, it changes one solution to another. So let's think about what instructions we're going to give, right? Well, what's the first obvious thing? The algorithm grabbed that quarter, so the optimal solution she is going to hold at the end of this iteration better have that quarter in it, right? So the first obvious thing to do is to tell the fairy godmother, hey, if you don't have that quarter, well, if you have that quarter, we're good, we're done, we can go home. Right? Everybody see that? If she already has that quarter, then we have no problem because she's holding an optimal solution consistent with what it was made before and just made. Right? But if she doesn't have that quarter, a good thing to say is, hey, you better grab it. Right? So the light purple is our new solution. But she's now holding more than 92 cents. Right? She's holding 92 cents plus a quarter. And so that's no good. So I say to her, hey, I have to have her drop that other quarter. Right? If she's holding another quarter, I tell her to drop that other quarter. Does that make sense? So it gets a little, and then she says, okay, I now have this new thing that adds up to 92 cents and its witnesses.
What happens if the algorithm wants to grab something and you try to tell her to change it, but there's no actual optimal solution that holds that thing?
Yeah, well, that's the whole trick. Yes, yes. So we're going to have to do much more, that was kind of the high level intuition, but we're going to have to be a lot more careful to make sure it's always possible. We have to do a lot of cases, right? It's proof by case. So one thing that's noted as we go through time, she's always holding an optimal solution, right? But we keep changing it. The prover keeps getting her to change it. So it starts off being an arbitrary optimal solution, and there are many of them that she could start with. She keeps changing it, and in the end, what will she have?
Optimal solution.
She'll have an optimal solution. In fact, which optimal solution? One that the algorithm is outputting, right? Exactly. He keeps making choices, and I learn more and more about what she's holding because what she's holding is consistent with the algorithm is doing, right? And in the end, I learn more and more about what she's holding, and in the end, I know what she's holding, and that will be what the algorithm has did, right? And so we'll know it's optimal. All right. So now let's talk about how we're going to give her these instructions to change what she's having, what she's holding, right? So we can do, it's going to be proof by cases, right? The first case is say, hey, the algorithm just committed to another quarter. Fairy godmother, if you're holding that other quarter, don't sweat it. Everything's good, right? Everybody get that? She happens to have that quarter. then she's holding something, and we know that it's optimal, we know it adds up to 92 cents, and we know it's consistent with what was done before, and we just checked and it's consistent with this new thing. Right? Everybody follow that? Right, that was the easy case. Otherwise, we say, hey, fairy godmother, we know you have this quarter and this quarter. Right? How do we know she has those? Right, because by the loop invariant, she's holding an optimal solution consistent with having those quarters. So she has those quarters. So we know, of her 92 cents, we know what 50 of her cents, but there's 42 cents that she has that we don't know what she has. Right? She has 42 cents that we don't know about. So we start querying about it. Well, that's more than a quarter, right? So, right, that's just what it said. She has more than a quarter that I don't know about. Right? They're different cases. Well, maybe of her 42 cents that we don't know about, maybe there's a quarter in there. Right? If she's holding this quarter, right? If this is her optimal solution and she's holding this quarter, but the algorithm grabbed this quarter, what do we tell the fairy godmother to do? Yeah, take this one, drop that one, right? Easy. All right. What happens? Maybe she doesn't have a quarter. Maybe she has 3 dimes, right? What do we tell her to do then, right? She has these 3 dimes.
Dropped it.
No, she not. So everybody, that's something to be concerned with. She doesn't have that. So what we have to do is we have to say, we have to be polite. Be polite to your fairy godmother. Right? So we say, hey, one case is she's holding 3 dimes. Right? Well, if she's holding 3 dimes, then what do? We massage it. What are we going to do? We tell her to drop the 3 dimes, take this quarter, and take 5 cents. Right? And we know, hey, fairy godmother, that wasn't optimum. All right, but whatever. Right? We need to check every case anyway. For every case, we have to say either it wasn't optimum, or we can, how do you prove it's not optimum? You massage it to something that's better anyway. So either way, we tell her how to change it. Right? That's what we do. She drops those, takes a nickel, and maybe she doesn't. Maybe she has 2 dimes and a nickel, right? And then we tell her to drop all of that and take the quarter that we want, right? Maybe she has a dime and 3 nickels, right? Same deal. Maybe she has a bunch of pennies, right? Well, it's getting worse and worse for her, right? And you just make sure that you've checked all the cases, and then in each case we give her instructions how she can change what she has. Does that make sense? So, we give her instructions and she's done. Now, we're writing this up. We got to keep track of the various objects. All right? The first object, we're at the top. Not objects as in the objects we're making decisions about. We're at the top of the loop. The algorithm has made decisions about some of the input objects, and we know the fairy godmother is holding an optimal solution, right? And then we just got her to change it into another optimal solution. So she's now holding, right? This is what we just constructed. She was holding optimal solution sub Li, and now she's holding this, right? She's holding this thing. And we need to prove, what do we need to prove about it? Prove that it's valid.
Consistent.
Consistent with what the previous decisions and the new decisions. And it's optimum, right? So valid, in this case, so when you're writing this up, which I'm going to have to read all of your write-ups, so you listen to me here. When you're writing this up, you're going to have a paragraph which says, hey, the fairy godmother, how do you massage optimal solution loop invariant into this? Now she's holding this, right? And now I have a paragraph which is going to prove that this thing is valid. What does valid mean? I need to read that you know what valid means, because half of you won't know what valid means, right? What valid means is that it adds up to 92 cents. So how do you prove that it's valid? Well, what we had before was valid. What we had before added up to 92 cents. we changed this into this, and we were very careful that any changes we made sure that it added up to the same thing it added before, right? If we took away 3 dimes, we put in a quarter and a nickel, right? So these two things add up to the same amount. This was valid, so this still is valid.
So you said that there's no feedback for the fairy godmother.
No.
So then how do we know that she was holding the wrong thing?
We give her options. We don't know what she was holding.
So then how do we know what was changed?
We know that we either changed it like this, or we changed it like this, or we changed it like this. And in each of those cases, we made sure that it was the same, right? If you go back to the chart here, right? In each of these cases, we were very careful that we got her to drop a quarter or add a quarter. Or here, except here she dropped 30 cents, we added 30 cents, right? And in fact, this case here, right, is exactly, when you said last class, it should work if every coin is a multiple of the others. Well, it's because we have this case that allows for that dime nickel problem. All right, so, right, I didn't need to go backwards, right? We check each case, the total remained unchanged. Does that make sense?
So is the fairy godmother really just actually holding some solution then, not necessarily an optimal one?
Well, the loop invariant says that she's holding an optimal one. In fact, we're going to get to that to the next consistent first. We'll get to optimal in a minute. Consistent. What does consistent mean in this case? It means that it has the same coins as the algorithm has, right? So this guy was consistent with the choices made when we were at the top of the loop, meaning it had this coin and this coin, right? Then we went around the loop, and the algorithm committed to this coin. So this was consistent, and we made sure that when we got her to do her changes, that we didn't mess up this guy and this guy, right? We didn't mess up the previous things, and we made sure that we got this guy consistent too, right? So if this was consistent with the previous, this was consistent with the previous choices, this is consistent with the previous choices and our current choice, right? Does that make sense? Optimum. How do we know that this is optimum? What does optimum mean in this case? Make sure you always tell me what optimal means, because I'll be looking for it, right? It's up in the question, but you'll be amazed how many people go wrong right there, right? You need to know what optimal means, you need to know what valid means, you need to know what consistent means, right? Optimal means in this case, minimum number of coins. Well, what do we know? We don't even know how many coins are in an optimal solution, right? But we know that this was optimum by our loop invariant. She was holding an optimum thing, right? And we massaged it into this, and we made sure that the number of coins never got bigger. Sometimes, okay, it got better, okay, she wasn't holding an optimal solution, right? But we're polite then. We say in each case, the solution never gets worse. It either stays the same, or if the fairy godmother wasn't doing so well, we got a little better. Right, does that make sense? So now, I'm going to be really looking for keywords. If you say, now I have an optimal solution, no, you don't have it, right? Now I know that the fairy godmother has an optimal solution, has a solution that's valid, consistent, and optimal, right? Then I'll be happy, right? If you put in those keywords, I'll be a little happier, right? Because I'm looking for any proof that you don't understand what's going on, right? And because she's holding something that's valid, consistent, and optimum, and is a solution, then we know the loop invariant's been maintained. Does that make sense? Everybody got it good with this?
Question.
Yeah.
So it's a final solution, right? So it's consistent with what? With the previous.
It's consistent with what the algorithm has done so far. Right? The algorithm has gone, now the algorithm at this point has committed to 3 quarters. Right? So she's holding something which tells you for every coin whether to take it or not. And what she's holding, we know is valid, meaning what she's holding adds up to 92 cents. We know it's consistent, meaning it has these 3 quarters that the algorithm is committed to. And we know that it's optimal, meaning it adds up to the minimal number of coins, whatever that is. Does that make sense?
So now, what if the algorithm is like, I want all quarters? Then, and you tell grandmother, you better have all the quarters.
Well, if all it does is grab quarters and it grabs $1 worth of quarters, then it's a bad algorithm. So I'm going to have a hard time proving it's right. Right? Sometimes your little brother goes crazy, and you have to, you know.
But then how, because you know it's 92 cents, so you would say it's over 92 cents.
Yeah.
Prover guy?
Yeah. Right. So I guess the thing is, when you have an algorithm, you have to either prove that it's always right using this method, or you prove that there's an example where it's wrong. For example, if it's trying to add up to, it has the 4, 3, and 1 cent coins, then it's trying to make up 6 cents. You can say, hey, the algorithm will be wrong. Right, so that was only one case. Right, let's start all over again. Let's say that we're at the top of the loop. The algorithm is committed to these 3 quarters, right? And the algorithm decides to reject this quarter, right? So she's currently holding, this optimal solution that is consistent with having these quarters, and the algorithm rejected the quarter. Now, what do we have to tell the fairy godmother? What did we say before? In this case, she's not holding that quarter. So, is there a problem in this case? No, in this case, we just say, if you don't have the quarter, then don't worry. She already has an optimal solution consistent with these no's, with these yeses and this no. Right? So we're good. Is it possible that she is holding that quarter?
Yes. Oh, no, it's not now.
No, it's not. Right? Now, in fact, I can say in general that it's not possible. Right? How do you know that it's not possible that she's holding it? Why did the algorithm reject it?
Yeah. Just some.
Because, right, the algorithm already had these, and she has them as well. Right? The algorithm rejected this because if you took it, it would no longer be valid. Right? So is it possible that she has it? No. Right? So often this case is easier. You say, hey, well, the algorithm didn't take it because if you took it, you would no longer have a valid solution. So, it would be no longer possible to extend it to a valid solution. Right? So she must not be having it, so we're good.
Why doesn't the algorithm talk straight to the variable? Like, why have a prover in between as we do?
Good question. The algorithm is your little piece of code that all it does is grab the next best object and commit to it or reject it, right? I mean, that's the algorithm. Right?
So where is all that code?
For the prover?
Yeah.
Good question. Where is the code for the prover? Anybody know?
No.
There is no code for the prover.
Yes.
We don't need to implement the fairy godmother. We don't need to implement the prover. It's all thought experiments so that we can prove it. It's math. It's not code. You might call this an algorithms course, but really, it's a math course. If you didn't figure that out already. Right, does that make sense? Alright, so I have to make sure that what she has is consistent with what the algorithm has done. And as we said, she can't have it, right? She can't have that quarter. That's just kind of what I said already. Alright, so now that proves that if we're at the top of the loop and the loop invariant is true, that there exists this optimal solution consistent with what the algorithm has done. and the algorithm commits to the next object, then I can prove that we can maintain the loop invariant. People kind of get what we're doing there? And as we go through more examples, I'll spell out more carefully. Okay, now you need a paragraph that says this. Now you need a paragraph that says this. And seriously, you know, maybe this is, you know, part of the reason I try to fail you all in the first assignment, the first test, is so that now you believe me. Right? All right. Now we have to do this last bit. You know, the last paragraph will say, you know, if the loop invariant is true and the exit condition is true, I do a little bit of things, I can get the post condition. All right? So what's our exit condition?
We have 92 cents with the points.
In general, it's we've made a decision about every object. Right? We've made a decision about every object. And which, you know, hopefully it adds up to 92 cents.
So I just wondering, do we have like finite number of quadrants and make those nice?
You know, this is a funny kind of example where I've been talking about an infinite number of them, and you know, your algorithm has to be finite, but I'm going to allow you to say, now I've used up, you know, I don't need quarters anymore, so I throw the rest away. Right? There are enough out there. Whether it's finite or infinite, I don't care. There's enough out there to solve the problem.
So I guess when we reach that point that we know that we can't take another quadrant and the frame mother won't have them.
Yeah, she throws, they're all, the rest are gone.
So we just switch to times then.
Yeah, switch to dimes, exactly. Exactly. All right, so the exit condition says what? The algorithm is committed to or rejected each object in the input, right? That's when the algorithm stops. What is the loop? All right, so we have a solution, right? That's what a solution is. It's a decision about every object. Do we know that it's valid? No. Do we know it adds up to 92 cents? No. But we know it's, from the exit condition, we know it stopped, right? From the loop invariant tells us what? Everybody should be able to say it. Everybody in unison. What does the loop invariant say? There exists an optimal solution consistent with these choices, right?
Yes.
So if there exists, what's consistent with, it must be, what the algorithm has must be what she's holding, right? Because if this makes a decision about every object, and this is making a decision about every object in the same way, it must be the same thing, right? And that then gives us, the code says just return what the algorithm does, and that gives us our post condition. What's our post condition? Right, post condition is that we have an optimal solution. Right? Does that make sense? Everybody good with that? You can see the algorithm's easy, the proof's a little hard. There's these various paragraphs you have to memorize. There's various tweaks that you have to put in. What are the only tweaks you personally really have to put in is you have to know what it means to be optimal. You have to know what it means to be, you know, what are the decisions we're making about objects? What does it mean to be consistent? You need to know those things. You need to know how I get the fairy godmother, instruct the fairy godmother to massage this optimal solution into some other optimal solution. You need to know who knows what. 5 minutes. Excellent.
For the post condition, would you have to say something like returns a solution whose sum is 92 cents and has the minimum number of coins? Do you have to be like
well, what the post condition is?
Yeah.
Yeah, the post condition is it returns an optimal solution, which in this case is to be, an optimal valid solution. So to be valid, it adds up to 92 cents. To be optimal, has the minimum number of quarters. Any questions about the big picture? So let's try to do the same thing again. All right? We now have a new problem. Oh, I guess we did this one already, right? This is the one we did, and we did all the steps, and so we're good, right? All right, so now let's try to do it again with a different number of coins, right? We have a counterexample, so we know the algorithm doesn't work, right? So let's try to prove it does work, right? The algorithm, the fairy godmother, we're at the top. Right, we're at the top, and the fairy godmother she's holding an optimal solution consistent with what's been done so far. Right, this is the optimal solution. Right, 3, 3. She's holding it consistent with what's been done so far. Why? Because we haven't done anything. Right, and then the algorithm. Right, she's holding it. then the algorithm commits to the 4-cent coin. Our goal is to instruct her how to change what she's holding into something else. Right? How do we tell her to do that? We don't know. It's impossible to do it. Right? It's impossible. Because it's not possible. Alright, so what's the running time of this algorithm? This greedy algorithm is very fast. Right? It has to first sort the objects. So assuming you had a finite number of objects, it takes n log n time. And then it runs through them and it just makes these decisions. Right? Very fast. Alright, so now you may all be panicking, but I swear you can all do this. Alright? You can all get perfect on this question. And I will tell you right now, there will be a question on the test in 2 weeks and 3 days. There will be a question then, and there will be a question on the exam. Right? Why would there be a question on the exam? Because half of you will fail it when you do it in 2 weeks. Right? And all of you will do great on it on the exam, because then you will learn that yes, you have to listen to me. But if you all listen to me now, yeah, actually, seriously, if you all got perfect on the next test, then I will take it off. I will put it on the exam. Right? Easy. All right. So it looks hard, but it's not really. Right? They're all going to look the same.
I'm confused as to how this algorithm is greedy, because it's not. If it was greedy, it would just take all the quarters, right? I don't understand.
Well, it has to be. It's greedy within being valid.
Right. So then, with that 4, 3, and 1 solution, it would take a 4.
It takes a 4.
And then it would tell the fairy godmother to make sure you have a 4 because I want to get to 6.
Right, but that can't.
You don't know that she doesn't know that she says that.
Right, but the way we prove that the greedy algorithm doesn't work is we say, well, here's an input. For a greedy algorithm to work, it has to give you the optimal solution on every input.
Right.
Right? So the input in this case is 6 cents, and what does the greedy algorithm do? It grabs the 4.
Yeah.
And immediately we say you're toast.
Who would say?
The prover. The prover will say, clearly this is wrong.
But there's no prover in the code.
Yeah, so that's why somebody could give you a piece of code, and then your job is to either prove it works or doesn't work. Right? So imagine you're the boss, and your employee gave you a piece of code, which is a greedy algorithm, and your job is to find out if it works or not. And so you have to do one of two things. You have to either say it doesn't work, and how you prove it doesn't work is you give me one input in which it gives the wrong answer. Right? In some ways, that's the easy case. To prove it does work, you have to prove it works for every input. And you have to do something like this. All right? So you're no longer, in this course, we're not the coders anymore. We're management. Right? We don't actually have to code, which is a good thing, because I hate coding. All right, everybody good? As I say, if you can't do, teach. Right, so, all right, so you're gonna have to go through one of these problems. It's gonna be a brand new problem that you've never seen before, right? And you're gonna have to give the proof, and it's gonna look, but really they're all very much the same. Now, to say they're all the same is do not give me the proof for the coin problem. At least 2 of you will. And I don't know what mark to give you. You give me the perfect solution for the coin problem. Okay, good. Right? And if it was the midterm, then I would not worry about it. I would just give you a 0 because I knew that you could redo it on the exam and it won't hurt you too much. But if it's your last course you've ever taken, you need to take, and I don't want to fail you, so don't do it. Don't do it, right? So you have to follow my proof structure. I'm going to tell you, I want a paragraph that says this. I want a paragraph that says this. Some of the paragraphs, not only they're identical to what I want, right? You just have to copy those paragraphs out. There will be small changes. The small changes are, you need to know, when I read your question, I have to know first, did he more or less follow the structure of my proof? Yes. Does he have it? Did he say anything so stupid I know he doesn't understand what's going on? Hopefully no. Is there evidence that this person knows what an instance is, knows what a solution is, know what the costs are, know what it means to be valid, know what it means to be consistent? Did they give good instructions on, when you're coming up with an algorithm, you have to know the greedy criteria. You have to know which object to get next, right? You have to know, do I keep it or do I not keep it, right? So that's how you come up with an algorithm. And you have to know if the fairy godmother is holding a solution, how do I change it into another solution? Then you have to say, I give her instructions. The loop invariant says that the fairy godmother is having this. I give her instructions to massage it into this. I want to see a paragraph with those instructions, how she changes it. Then I wanted to say, yeah, now she's holding something else. And then there's a paragraph which says, yes, I know it's valid. How do I know it's valid? It is, well, what she was holding before is valid, and my changes didn't make it invalid. Right? What she's holding, and when I read this paragraph, I want to know what does valid mean. Valid means, in this case, it adds up to 92 cents. I want to make sure it's consistent. What does consistent mean? It was consistent. What she was holding was consistent with what the algorithm had done so far. The algorithm did one more thing. I made sure it's still consistent with those things. I made sure it's consistent with the new thing. Hence, what she's holding now is consistent with what was done before and what was just done. People kind of getting this? I really do talk fast, but we're down to 1 minute. All right, optimum. What does optimal mean? Right? It has the best value of all solutions. It has, the minimal number of coins. Well, what she was holding was optimal, and I made sure that the number of coins either went, probably stayed the same, but possibly went down.
So the 431 example would fail at optimal, right? If he told you, just drop the two 3 coins and take a 4 and 2.
Right. Right. It could change. It could fail in optimal. Maybe it would fail in valid. Maybe it would add up to 12 cents. Right? Maybe it would fail in consistent, and the fairy godmother says, "Hey, I really want valid and optimum, so I'm not going to do what the algorithm told me to do." Right? It could have failed in any of those ways. And the rest is the same. Right? So you have to make sure that you understand these steps and memorize these steps, and then make small changes. All right, so think about it. Over the weekend, we're going to have a test on Monday, so make sure you review the loop invariant steps. I told you there was that one graph, those 2 graph theory problems in the book, which are a little harder than we would do on a test, but not, hugely harder. And then also, if you have time between now and next Wednesday, make sure you go over these things, read the chapter in the book, try to understand it, because if you do your best to understand it, then we go through examples. You can say, yeah, I get it, and you'll do perfect.
Did you wear that shirt just for the slides today?
Yes.
No, I didn't give it any thought. You might notice I wear fairy shirts a lot. In fact, I was just, last week I was in the secretary, and she says, "Are all your shirts purple fairy shirts?" I said, "No, I have some red ones." All right. Any other questions? Everybody good? We'll see you here. So next Monday, I don't really like those tests because they take up a full hour, and it means we talk faster. But so the hour before and the hour after, we're going to play that same game, and everybody's going to do brilliantly. Good.